We've talked about cis-trans isomerism in the cycloalkanes. We also see cis-trans isomerism in alkenes because of that double bond. The double bond can't rotate. So if we look at these molecules, 1,2-dichloroethene and 1,2-dichloroethene, they both have a chlorine on the 1 and the 2 carbon, but they are different, aren't they? One has the chlorine groups on the same side of the double bond, and the other has them on the opposite sides. So here's a model of trans 1,2-dichloroethane. Pretend there's a hydrogen atom here and here. They're on the opposite sides. With ethane, 1,2-dichloroethane, you can just rotate the bond between the two carbons, and there's really no isomers. There's conformations, but this I cannot rotate. The only way to make it into the cis isomer is to break a bond and reform a bond. Now I have those chlorine atoms on the same side, sisters on the same side of an argument. They're on the same side. Trans is across. These isomers have different physical and chemical properties. The cis isomer boils at 60 degrees, melts at -80. The trans boils at 47, a lower temperature, and melts at a much lower temperature. We don't need to get into why, but I just want to point out to you these guys are different. These are geometric isomers because they cannot be converted just by rotation around the double bond. They can be separated, they can be isolated. If you have a mixture of the two, you can separate them based on their physical and chemical properties. You can convert trans to cis or cis to trans, but you have to have enough energy to break the pi bond. It doesn't just happen under normal conditions. So which of the following which of the following compounds can exist as cis-trans isomers for other structures? Well, we kind of just have to start drawing to figure this out. I wouldn't expect you to look at the name and be able to figure it out. 2-pentene. 5 carbons, right? 1, 2, 3, 4, 5. And the double bond is between the second carbon and the third carbon. Now, when we're looking at cis-trans isomers, we want to see very clearly what's attached to the carbons on the double bond. And so over here on the end, that carbon is going to have 3 hydrogens. And then it's going to need a hydrogen here to have its 4 bonds. The other carbon also needs a hydrogen. And then this is going to be CH2, CH3. Are these hydrogens on the same side or on opposite sides of the double bond? They're on the same side. It might be a little easier. This is, you could call it cheating. It might be easier if you draw it in more of a trigonal planar arrangement where now we can see this is the triangular and this is triangular here. Now we see that the H's are definitely on the same side. Here we've got a methyl group and there we have an ethyl group. Is there going to be another isomer? If I exchange the methyl group and the hydrogen group, is that going to be different? Yeah, it will be. Because now, are the hydrogens on the same side or on opposite sides? They're on opposite sides, right? So, I shouldn't leave my answer like that because that's only half of it, so I better draw the other one back in here. And put them on the same side. So there are cis-trans isomers. 3-heptene. 7 carbons. 1, 2, 3, 4, 5, 6, 7. Yikes. 3-heptene. There's a double bond on the third one. So this is going to have a hydrogen. That one's going to have a hydrogen. And this guy's going to have 2 hydrogens. That one's going to have 3 hydrogens. Are there cis-trans isomers for that one? Yes, there are. In order for us to have a cis-trans isomer, each of these carbons has to have 2 different groups on it. If both of these were hydrogens or if both of these were ethyl groups, then it wouldn't matter. But one's a hydrogen, one's an ethyl. Over here, we've got 1 ethyl and 1 propyl group. The 2 groups attached to the carbon are not the same, and so we do have isomers. And I didn't leave any space to draw it, so I'll put it maybe way up here at the top. So we could have the ethyl group across from the propyl group. So these 2 guys are the answer to letter B. Any questions?
Sorry, Judy, how did he pick the trial of the conversion?
Because I look at this, and here I have the hydrogens on the same side, and I can put them on opposite sides of the double bond, and it's different. Okay?
So you're purposely trying to draw them opposite?
Yes. Because it's asking which have cis-trans isomers and draw their structures. So if there are cis-trans isomers, you draw one that's cis and one that's trans.
Are they the same structure, or do they have different?
They have the same molecular formula, the same molar mass, but their chemical and physical properties, like their melting points and boiling points, will be a little bit different. Because this puts a kink into the structure, and so it can affect how straight it can be. It can affect the intermolecular forces, do all kinds of things. Any other questions?
So they're both can exist as cis-trans isomers?
Yes. Yep. So letter A has this trans isomer, and this would be the cis isomer. And letter B, 3-heptene, this would be the cis isomer, and that would be the trans isomer. Any other questions? Questions are awesome because I cannot anticipate what little piece I left out that is causing you to not understand it.